Hi everyone and welcome to today's session. So today we'll be covering a very interesting and important paper called the Hierarchical Reasoning Model. So what this paper is claiming is that a very small model, like in their paper, is 27 million parameters. And this model is able to, based on just training on data such as the ARC-AGI challenge, is like the IQ puzzles. You have an input grid, output grid, and then you try to find the relation. And later we'll see some pictures of that. ARC-AGI challenge, maze navigation puzzles, which is like from the start state to the end state, how to navigate through the maze, and Sudoku puzzles, which is how to fill up the board 1 to 9 with rows, columns, and squares, having only 1 to 9 individually, no repeats. So this kind of puzzles are actually difficult for large language models because, as you know, large language models don't really do this kind of robust rule following quite well. Mathematical logic following is not that great. But using some form of transformer model, but in a recurrent manner. So while they pass through the transformer layers, they have one layer that is called lower layer and one layer that's called higher layer. So they go through the lower layer multiple times before going to the high layer once. And then they repeat this cycle multiple steps. Eventually from the high layer, they will go out to the output layer. And this hierarchical reasoning model, just by making the transformer architecture in a more recurrent manner, and not just any normal recurrent manner, is a recurrent manner that has more recurrence at the lower end and a little bit of recurrence at the higher end. So it's like you update the lower part more and you update the higher part like lesser. This kind of thinking enables the model to outperform large language models like OpenAI O3 Mini High, and also for Claude models as well. And this is quite interesting because such a small model of million parameters can do as well or even better than billion parameter models just by fine-tuning on that data. And just of note, that data that they fine-tune on has no human annotations needed. So like for the large labs, normally for ARC-AGI, maybe you have some sample code, some sample reasoning steps that maybe people fill in themselves, like they write model answers. This hierarchical reasoning model does not need any of this chain of thought reasoning. It just operates at the input level, which is the grid level, and iterates over the grid level, and the output is the grid level. So you can say that all the thinking is done at the grid level. And that's amazing because, you know, a lot of reasoning models right now, O3, Gemini, DeepThink, Claude, Opus, those kind of models that use thinking or reasoning typically uses human language as a way to think. Okay, so I'll explain more as we go through the slides. And this is just a new way of doing thinking in the latent space, not in the human language space. Okay, so without further ado, let us begin the paper. And kudos to these guys from Sapient Intelligence. They're also from Singapore, just like me. So I think this is a great step forward to, you know, for even non-big countries like US, China, you know, as long as you have an idea, you can iterate with small models, get some ideas out, share them open source. Thank goodness it's open source. So I believe a lot in the open source culture. So this is a great step in that direction. And so we can learn a lot from these papers and we can improve our understanding of the current transformer and the LM era. All right, let's move on. So this is the results. So the results show that, you know, just this model, 27 billion parameters. Look at this. In the ARC-AGI 1 challenge, it wins Claude 3.7. It wins O3 Mini High. It wins the transformers without any recurrence. This is called direct prediction. Basically, just using a transformer architecture alone, it just gets 21. But with the hierarchical model of low and high level thinking, it gets 40.3%. That's like 20% improvement, 19% improvement. DeepSeek, I think don't use. DeepSeek is not that great in terms of this kind of benchmark. So this is something that is quite remarkable because this model itself is only trained, okay, but this height is only trained on the ARC-AGI. Great. And actually it's only trained on that problem. Okay, if you look at the way they train it, it's not a generic model. It is a very specific model trained to solve that only one question. All right, and that is something that is a bit different from the models of today. Models of today are meant to be very generic. You train on a lot of data, it solves for a lot more. So, you know, you might ask, like, is it generalizable? I don't know. I mean, like, I think it's generalizable within that problem domain, but definitely not generalizable in the sense that you can do any kind of problem. So, if you want to talk about AGI, artificial general intelligence, you're supposed to be able to do anything that a human can do, or like even beyond that. I do think that AGI is actually a misnomer because I don't think there's a general intelligence. Like the intelligence is grounded to your action space, to your input space. If you want it to do something, it needs to be grounded well in the action and the input space before you can do it. Like, there's always this thing called, to solve a problem, you need the right tools. Okay. And yeah, if you want to get AGI, you definitely can't do that unless you have all the tools in the world. And unless one day computer can come up with their own tools, like invent their own code, this may not be a great term to use. But one way that OpenAI is clarifying AGI is that it's great at some human tasks, and you can define those tasks. Then maybe I think that is possible. Okay, but definitely if you talk about HRM as AGI, in that sense, they can do general tasks. No, it's not. It's a specialized, highly specialized model meant to do a certain task really, really well, and it can do it without human annotations. Okay, so this
But
is yes.
but Chong, one way to think about it is like, if is the architecture good enough to be able to be applied to a whole bunch of problems without much underlying changes to the structure itself? Like the transformer model, the QKV matrices have not changed in a long while. For vision, you have convolutions that have not changed. Like, but it can work on any kind of image. The same way, this architecture, it seems like it is being applied to very specific problems, but it's still able to consistently do better. It is quite generic in that sense, but again, AGI is an extreme word, I would agree.
Definitely. So I think this is amazing that it can really outperform by being a very specialized model. And it kind of shows that, for this kind of challenges, maybe being general is not a great idea because like these challenges maybe is specific to that problem itself, a specific constraint. So if you train on all general stuff, you might get contaminated. That may be the nature of this kind of stuff. Like Sudoku also, you just want to focus on that bot. You don't want to think of like maybe other bots, although other bots might give you some insights as to how to solve it. Yeah. But generally, this kind of problems, the main focus is only on that board itself or that maze itself. Given that maze, without any other factors, you should be able to solve it. Okay. And one other thing that is brought up is that yes, you can train it on very few training examples and it can perform very well. This kind of reminds me of, back in the days when we were playing Atari game playing, there was this thing called the Deep Q network by DeepMind. And basically, what they did was that they used one network trained over one single game a lot of times, and it surpassed human behavior. So this is definitely not AGI, but it kind of has some analog to this work where you just train on one single domain with many examples. Actually, not really a lot, but like 1,000 examples. You can already get superior performance. Okay, so maybe you don't need one model to do everything. You can have a generic model, maybe a generic model, we just call it GM. And then you train at different problem tasks. You can train at problem one, you get a model one. You train on problem two, you get model two. You train on problem three, you get problem model three. So this is basically you from where you find from how you fine tune, you get multiple specialized models. Yeah, maybe that should be like how we think about doing stuff that solves problems more effectively rather than taking one model to solve everything. However, if the problem is in the pre-training space, you can use the general model. Yeah. So I mean, what this shows is that fine-tuning, and if you fine-tune really well, you can outperform the other models. So to me, it's not very clear. Okay, other than this direct prediction thing, because they fine-tune it, it's not very clear for all these models that are closed source, Claude 3.7, O3 mini high, what will happen if you fine-tune it well? Okay, will these models perform better if given the same fine-tuning data that HRM is given? Because they are not trained the same way, you see, like they only use the API, they did not like fine-tune it further. So it could be the results are due to the training, okay, rather than due to the model being better. But definitely, if you compare to just without the recurrence, there is a significant improvement. So there's something in there in this model. It's just that the results, because of the lack of like direct comparison to this closed source models because they don't have access to it. Or I mean, you can also fine tune these models, but they didn't do that. So if you just because this was taken directly from the leaderboard from the ARC-AGI. So if you are going to do all this, you may not be able to discern how much of the performance is due to the pre-training, the fine-tuning data, and how much is it due to the model. Okay, but that aside, just by looking at the performance itself, it is noteworthy to see how this works. Right. So I'm not going to go through the rest. The rest of it, ARC-AGI 2 is a significantly harder problem than ARC-AGI 1. And you can see that out of like problems tested, like O3 mini high only did like 3% of like I think 1,000 data points, right? But HRM can do about 5. So that's pretty amazing because this is actually quite difficult, right? Of course, some people might say that there are other models that can do like 8%, 9%. I think Claude Opus can do 8%, like in the latest leaderboard. But those models are huge. To get 5% here is actually quite remarkable when the direct model gets 0, right?
Yeah.
You can see for like very difficult logic puzzle following kind of thing, only HRM can solve it. So there is something here because traditionally we don't solve logic puzzles with LLMs. They are quite a bad fit. But there's something in this architecture that looks like it works. So
Yeah.
before we move on, any questions, clarifications?
I kind of just wanted to add something, if you don't mind. So I think in the ARC-AGI one, it's like you pick one out of four correct answers, and you can luck out with a in token space thinking with an O3 mini high to pick A or B or C. Whereas in the other ones like Sudoku, even if you get one cell wrong, it is still a wrong answer, which explains why it would all be zero, right? Whereas
Okay.
getting such a high number is a pretty good deal. With near perfect accuracy is a big deal. And I think the official ARC-AGI1 results and the holdout set has not come out. I think this is still being trained, the eval set results, but it's still nonetheless a very special moment, I feel.
Yeah. So just a clarification here. Actually, the ARC-AGI challenge, because I did it before, it's not MCQ. It is still you need to output the entire grid and you need to get all the cells correct to get it right. So it's not as simple as an MCQ. I mean, some papers might make it easier like MCQ to help the model solve better, but the original task is difficult. It is not easy for people to do. So one thing that why is it like can solve more ARC-AGI compared to Sudoku? Maybe the fact that this kind of puzzles for ARC-AGI are more like grid-like in nature. You shift the grid from one end to another end. People have seen this in competitive programming questions for some of them. Whereas for this kind of Sudoku, in order to fill this out properly, you need to do like if-else logic and so on. Unless you use the LLM to create a computer program. Actually, there's this algorithm called the dancing links algorithm that can solve a Sudoku grid perfectly. Yeah. So if you ask the LLM to generate a computer program, I'm sure all of them will score like almost full marks. Okay, but but the thing is, the way they evaluated the LLM is to evaluate it in language space. And if you want to solve a Sudoku in language, you try solving it. Oh, the first row here, I'm missing the numbers 1, 3. I'm missing the numbers 1, 2, 3, 7, 9. And this row, I'm missing these numbers. And then the other columns, I'm missing these numbers. And so, if I were to combine the two rows and one row and column, you see this number here is maybe a 50% chance of number X, number Y. Can you see that if you reason it in language, it's going to take a while. And so the natural way of reasoning for this domain is actually not in language. Whereas for ARC-AGI, actually, there's this thing called the language arc, where I think it's language arc, where they basically condense a puzzle into an instruction. So like, for example, this puzzle here could be, um, fit the fit the cells by matching the red parts. Okay, this is actually difficult, by the way, because it's not just a direct matching. There's still some form of optimization here because you can see that these two parts need to match with these two here. These two needs to match with these two. It's not obvious at all. Actually, it's an optimization problem. It's not a. In fact, even kids might not be able to solve it because it's not easy at all. Yeah, I don't like this kind of puzzles for ARC-AGI because it's more like logic puzzles. It's not really testing human understanding. It's more like IQ puzzles, like those kind of like fit 7 blocks into a square, It's not easy. And But there are a lot more puzzles in ARC-AGI that are like literally shift the square from left to right, that kind of puzzles. Easier for language models to use language to reason. Here, you want to language reason this part is difficult. This is an optimization problem. It's difficult to use language to optimize this. Okay, so again, the problem domains shown here are more optimization based, less language understanding, and it's impressive that a transformer can do it. Yeah, it's impressive that a transformer. I never would have thought the transformer can do this kind of optimization problems. It's always not using a transformer. So later I'll go through. So like I think there's something in this low and high level reasoning
Yeah.
that simulates an algorithm. Yeah, maybe algorithms are of that form, of that nature. Yeah, who knows? Maybe that's a generic form of an algorithm. Yep.
I think in the later part of the paper, they kind of think briefly talk about the kinds of algorithms, the inner representations, come out with when they try to inspect it and
Yeah.
see, especially in the path maze navigation and Sudoku, like what is it actually trying to solve? In my mind, I would be like the Q, KV, and matrices. Like the lower level is asking questions like, what are the nearby cells? Am I constrained? What is my row? What is my column? The higher level module is like, which part of the Sudoku should I focus on next, and things like that. That's
Yeah.
maybe the kind of query that's coming out, and the key values are coming out. Yeah.
Yeah, actually, since we're on this slide, we might as well cover this first. It does matter. So you see, like for the maze also, it's an optimization problem. You need to find the path to the end. This is humongously difficult. Okay, even if you use like a breakfast, like you use a brute force search, it's going to take a while. In order to do this well, you kind of need to use stuff like I just leave out some A star search, breakfast search. Depth first search is probably not a good idea because you might go to the whole maze and not find the answer. So you can use searches like this to solve it. So definitely not a large language model problem. So how does this how is this fed into the hierarchical reasoning model? So hierarchical reasoning model, so it is basically a model where maybe I just go through the model before we go through. It goes through this input space, you embed into tokens, just like a transformer model. It goes through a low level model. So basically, this L module is a transformer. So it's basically, it has attention inside, multi-headed attention. And then at the end of it, it will come out with a logits. But in this case, it will come out with normally it comes out with a logits at the end for the output space. But here it just outputs a latent space. And there are two different latent spaces. One latent space is latent space low, and the other latent space is latent space high. Okay, this latent space low. So why latent space low and why latent space high? Okay, so in this paper, they actually talked about how it maps to the brain, all right? So in the brain, it seems that there are different areas processing different parts. So there are low frequency oscillation areas that does more low level processing, and there's higher level cognitive areas that has a like lower wavelength, don't process that long, don't process that often, but it's necessary to have both of them together to do it well. So taking insight from neuroscience, you have a low-level module that keeps being invoked every time step, and then you keep updating your hidden state here to be more and more expressive to this input. So this is basically, if you know recurrent neural networks, recurrent neural networks work in typically the same way. So I'm just going to draw a diagram here. You have an X input here. X is your input 1, and then you have a hidden space here. Let's call this hidden space H. And then you typically have an output space here, Y. So like after the first hidden state, you get output Y1. Then you feed in the next hidden state here. So this hidden state 0. Then you feed in the hidden state 1, you pass through your recurrent neural network again. You pass in the next input X2. And then with the X2 and the hidden state here, you get your output Y2. And you can keep doing this all the way. You just pass in your entire input here, you get your entire output here. You can keep doing, actually, if in most cases you may not do something like this. Sometimes you might also pass in the entire input sequence first, then you take the output. So basically, just to modify this diagram a bit, like sometimes maybe you can say that this is the done token. Okay, only at the done token here, then you start to output your Y1, Y2. That's also a possible way of doing this recurrent network. So basically the idea is that, you just keep outputting until your model says N. Yeah. Then you can take this. So if you want to do sequence-to-sequence transformation using recurrent neural networks, it's possible. You can just take in your whole sequence here and then it output here. Or the other way to do it is to output something every token here. That's also possible. Like that's if you want to do okay, so actually different ways of doing it. Like if you do it in this way, typically what is done is like, okay, let me just erase this thing here. So if let's say you want to take in your whole sequence here, and then you want the model to output something at the end, usually what will happen is that after done, your Y1 will come here as an input again. Yeah, so that's how you like, if you want to do like sequence to sequence transformer style, you can do the output here and put here. It's something like, your transformer, you have your input and your output tokens conditioned to get your next token. You can do that with a recurrent neural network as well. Okay, but why is this not used right now? So I have a video on this actually. Like, why is this recurrent neural network not used right now? It's because this hidden space vector, okay, in RNNs, the hidden space vector typically is overloaded because okay, let's just use a very simple example. Like you just keep thinking of, for example, if I ask you to remember a sequence of digits, like ask you to remember 1, 3, 2, 3, 6, 7, 9. Initially you might remember everything. That I force you to output this series of digits into a 2-digit number. So of course the latent space is not like a 2-digit number, but just for example, this is your input space. The more numbers you put in your input space and you force yourself to output into a 2-digit number, maybe at first your 2-digit number can be like 1 and 2, so you can store as 12. But then once you get 3, 6, 7, 9, maybe in the end you only store like 7, 9 because you are forced to lose some information. Like this input space here are all with the same like vector dimensions as the hidden space typically. Of course, you can make your hidden space bigger, up to you how to change the architecture. But there's a fundamental limit as to how much your hidden space can remember. And so RNNs are typically lost out in favor um, to transformer networks because transformer networks with the self-attention here, you can put in your entire space here, x1, x2, and then in the end, your y1, y2 for the output. You can put this through here, and then out comes the logits. So like maybe here, no prediction, no prediction. Then here you predict y1. Then, here predict y2. And then this y2 goes back here to the next time step to predict the next token. So with a transformer, you are able to preserve input token, meaning because you can pay attention to any one of them. So I didn't draw the other arrows for attention, but with causal transformers, your next time steps, you can use the earlier time steps to predict. Like for example, you can use this one here to predict the next few tokens. So essentially, you don't have this problem of recurrent neural network where you might lose information because you don't have this compression needed. You can always pay attention to the earlier tokens and you have your full information there. Okay, so why are we going back to RNNs? Why are we going back here, right? So here, this architecture is like an RNN. Okay, it's the only difference is that instead of like one hidden space, you have two. I mean, of course, you might argue with me that, hey, it's not only this architecture that has two. What about LSTMs? Long short-term memory. Like they also have two hidden states. One, the forget gate, one is the normal hidden state. Why? What isn't this like LSTM? And the answer is yeah, similar, but in LSTM, your model, your whatever they do in this encompasses two of them. Like both the low and the high will go through the same model, but this one, no, the update is very specific. The update for the low just goes into the low module. The update for the high goes in the high module. There's no like overlap here. So there's something here that is done that although there's some loss here, okay, but this is a hidden state. Okay, this is a hidden state here. And just to give some understanding of why this does not suffer from the lack of um, compression space problem, is because this model, instead of being a neural network, this model is actually a transformer. So while compared to traditional neural network, this is a neural network. This model here is a transformer. What's the difference? Okay, actually, the transformer can take into account all the previous inputs. So let me just delete everything here. This transformer itself can take into account the entire input sequences here as the input here. So every single stage here, you get the entire input sequence. So, gone are the days where, you forget your input state because the input state is given to this transformer. But we are saying that, hey, I don't want to just give the input state to this transformer. I also want to give it extra guidance. And this is the guidance, extra guidance. Okay, this is extra guidance because you have your entire input space already given at the bottom here. Okay, so this basically is something that is quite different from this architecture to the RNN. Also, if let's say the paper orders listen to this, you can correct me if I'm wrong. This is my inference based on the code. So if let's say this is wrong, then
No, this is
yeah,
true. I agree. This is great, and it's amazing how they also bring in the benefits of the recurrence and try to get rid of some of the problems of RNN and keep the best of both worlds. So it seems like the right way to start approaching this problem. Yeah.
yeah. So there's two extra guidance. There's a high level guidance also. So you can see in this high level guidance module, there's no input. So you see the input came here going to the L module, but the H module only takes in the L module. So at the high level, does not get access to the input layer. So there's some form of hierarchy here. So it's like you can say that, oh, the low level processes the input data with some guidance steps as to tell you, oh, maybe focus on focus on objects. Like for ARC challenge, maybe you can say focus on optimization paths. This guidance here, I mean, if we could read it out in English language, maybe that's what they were saying. So this extra guidance tells it to like prompt it to guide the transformer to process in a different way. All right. But this high level module here, it's not taking in the input direct, at least not in this path here, and also not in the code that I saw. This high level guidance is basically taking only the low level module and processing what the low level module has processed. So it's like a next step in the understanding. And yeah, it's quite amazing because like in the end, it is from this high level module that goes to the output head. I'm not sure whether there's one more here, but I don't think so. I don't think there's an input layer to the high level module. So it is like a digested information and goes out to the output head. And like to me, this is something that is quite interesting because like this might be like the way that you split your understanding of the input. Okay, let me just do one quick check because I just want to make sure the high level module does not get the inputs because
It does
in
not. So the input is an MLP. There's a projection into the lower level module only.
so this is the input. So at the high level module, there's no input. So this is amazing because this means that whatever grid information that is digested here in the low level module is only passed on in latent space, and the output here can get back the grid. That's amazing to me because like I always felt like if you want to get back the grid output, you better give it the grid input. It doesn't need to. This model shows that you don't have to, and it performs better than a direct transformer prediction. So if let's say I were to put in my input layer and I go into the module, which is the normal transformer module, you maybe go through your tokenizer, your embedding, and then you go through your transformer here. I just called it a transformer, and then you get your output. So like without this architecture, just using the input, going to the transformer, you get the output in terms of your tokens. You don't get a very good performance compared to this. So that's something interesting about the low level processing and the high level processing that leads to a superior performance. So you can see the performance here again. The direct prediction is like 19% less than the HRM, and the direct prediction can't even solve the rest. So there's something here about the low and high level thing. So I mean, while we go through the thinking thing, I just want to highlight the neuroscience inspiration here. So like the brain has some form of hierarchical processing. High level integrates information over longer time scales. Low level handles more immediate information. This is reflected in the low level processing module you saw in HRM, which updates at all time steps, and the high level just updates every t time step. So it's a bit slower in updating. There's temporal separation. They operate at distinct timescales, like theta waves and gamma waves. So the meta representation is a lower hertz, lower representation is higher hertz. I mean, people have done brainwave mapping. This is actually true. If you are focused on task solving, your gamma waves will be higher. You will try to focus more on the task. But if you are more like deep meditation, your theta waves will be higher. So not alpha waves, theta waves. So the slower waves will typically be more apparent when you are doing high level cognitive processing. So I think this in general is quite true. Um,
I think there's a lot of precedence to this. Numenta and Jeff Hawkins has been talking about this for many years, and they also have a hierarchical temporal memory based neural network architecture, but they could never get it right because I think the fundamental blocks being transformers here is really adding to the quality of the performance. But I think the neuroscience inspiration has been there for a while, and these guys have been able to crack it. Yeah.
yeah. So there's something here about the low and high level processing. And this recurrent connectivity is also true. Like when you talk about how the brain lights up like a Christmas tree during when people are thinking about stuff, um, because people have tried to measure consciousness in the brain. Although right now my view is that consciousness may exist outside of the brain, but there's neural correlates of consciousness in the brain. I mean, we can only measure the one in physical. So we talk about the physical representation of consciousness. There is recurrence, okay? Because one brain area lights up, another lights up, and then they like as though they're talking to each other. The whole thing lights up like a Christmas tree if you look at the fMRI scan.
And you can literally see there's a lot of back connections going from one region to the other. There's like literally a loop circuit that
Yes,
people
yes.
can observe. Yeah.
So like even for the visual cortex, they map out V1, V2, V3, V1, V2, V4, and so on. And in fact, to the thalamus and so on, there are recurrent loops everywhere. So like the V4 area can actually go back to the V1 area, and the thalamus or the amygdala can also go back. There's so many different recurrent loops, thalamus and so on, like cortex. So in fact, I don't think our brain map is accurate. Yeah, because there's just so many connections, and it's so tiny and small, right? How are you going to map everything? And how do you know this area is what? This is how do you know this hippocampus is the prefrontal cortex? It's like, someone just took a line and say, hey, this is the prefrontal cortex. But actually, in reality, the brain looks almost the same everywhere. Yeah, so you need to, in order to know like how this is done, like recurrence, we know there's recurrence. But to say that this brain region maps to this main region is a misnomer to me because brain regions are artificially created. There's no boundaries in the brain. Like the brain did not say that, hey, this region is your amygdala, this region. That's just human scientists trying to classify the regions.
And then it's also so elastic. Like say if somebody has an injury in the vision back of the head, they lose the sense of vision. Another parts adapts and they start using that as the vision region, and so that also says something. Yeah.
Yeah. So these three things in neuroscience, I believe they are true. And I do think that is expressed in quite a direct way in this architecture. So let's just sit this in here for a while. The rest, do you have anything you want to add on before we go into like how this low and high level modules view the input grid?
Yeah, quick note. This is from a while back. The first slide that we're looking at that had the training examples and the different models and their performance, if you can go back to that slide.
Yeah, sure.
Um, so we were discussing the performance differences between the HRM and the normal pre-trained models like Claude and O3 MIDI. But my understanding of the paper is that the HRM performed off of just pure training. It didn't have any previous pre-training or fine-tuning or anything like that. It was a raw model given only about 1,000 examples, and that it immediately outperformed general billion parameter models immediately on the spot without any other type of training. It was
Mm,
just off of that 1,000 examples fed to a raw model that was,
yeah,
randomized and everything.
you're right.
That's my understanding of the paper. I just wanted to clarify that. So really, that just goes to show the performance is much greater than what we were previously talking about because this is without generalization. The model hasn't even done generalization or anything like that. It's just been shown 1,000 training examples and immediately picked up on all of the features it needs to extract and understand to problem solve at the level it can because it's a very small model, 27 million. But this level of performance working with that little parameters is very impressive. Was what excited me the most about the paper. But I just wanted to clarify the training examples. It was
Definitely.
pure, yeah, it was pure training. There wasn't even fine tuning involved.
Correct. So when I used the word fine tuning earlier, I was just using the lingo that people normally use to talk about model training. So indeed, when they initialize this, they use the Yann-LeCun normalization init for the neurons, and basically from then they just start training on the 960 samples for ARC-AGI one. And I mean, you think about this way, you can say yes, you don't have any fine tuning, you use pre-training, but it's actually the same thing. Fine tuning and pre-training. It's just depending on how you view it. So you can say that, yes, these are just pre-training examples. No problem, you can use that term. But what I want to just say is that while you might think that, yes, okay, I only need to use this to get performance, I have a feeling that if you mix examples together, you get worse performance. Because as of now, the model has no way to say, hey, this is task one, this task two, unless you use a token to say this is task one and this is task two token. Then maybe that can work. But as with models, the more data you feed in, maybe this parent model may not be enough to store all the data. It's like, you have to be forced to memorize words in the dictionary with a limited hard drive. Like after a while, you might get out of there's not enough memory to store it. So perhaps this may not be enough to store all the examples. So this works for one example, one problem, and then you give it more different variations of that problem. But I'm not too sure whether it will work if you store all the answers to the different problems in the same model. There might be an overload. So pros and cons. These models here from industry standard, billions of parameters, but can solve a generic task of problems, a generic suite of problems. HRM cannot. HRM is solving one particular problem really well. So I mean, I'm sure we can extend this model. Later we will talk about a slide that I have. I think this can be extended, right? So Derek, I think you're right. This is just trained, like you just randomly initialize with some initialization. In this case, they use the Yann-LeCun style initialization, and then you just fine tune on the examples.
Okay, understood. Thank
Oh,
you for
sorry, I
the
used the word fine tune
clarification.
again. Yeah, you can use.
Yeah,
Yeah.
no,
It's
but
just train. Just say we just train on the examples. Sorry, let's not use
we
pre
train.
fine tuning. Yeah, there's no different pipelines here. There's no RLHF also.
Yeah, no. It was just a clarification on the terminology because, like you said, the argument doesn't really matter the terminology. It's just the training.
Yeah, it's
The
just training.
what it trained on it than what the performance was already.
I'm
Right.
sure. I think we're going to talk about how it trains on every example here, but it looks like it takes each problem and spends a lot of time. The forward pass is not very simple. It's just thinking a lot about the problem before finally, giving out a prediction which gets compared to the correct answer by the loss function. So you look through and take a lot of time thinking about every single one of them. So I think it still takes a lot of time to train. It's not like you train for a few minutes and you're done.
Yeah. I think 10 over hours in a CPU set. I mean, in a GPU setting. Yeah. So this basically are the tasks. So I'm going to skip the first few slides. I'll get back to them later. I think it'll be interesting to see how the low level head, and the high level head views how the intermediate time steps are. So these are the problems. And yeah, just to put a caveat here, there's a lot of data augmentation done. They take the input output example pairs, augmented by translations, rotations, flip, color permutations. So basically, it's like saying that, if let's say there's a square here, the red square input grid goes to, maybe you mirror it at the other side, red square. So this is your task itself, the training example. So we do color invariance. Okay, so basically we do okay, now this is a green square, and then you flip here. So people have done studies. If you do the ARC-AGI challenge, you augment it like this, actually improves performance drastically because there's too few input examples in the ARC-AGI challenge. So if you augment it, easily 20-30% problems improvement is possible. You can also augment with symmetry, rotation, and so on. That's what they did here. You can even translate the puzzle a bit, but translation has a bit of an issue because, if let's say this is a mirror image puzzle, you translate it up and down is okay. You translate it left and right, it's not okay. Because if you translate this square to the right a bit, it's like if you translate this square to the right like this, and then you translate your output square to the right, then it's no longer a symmetry puzzle anymore. So this part here needs to be done in moderation. Yeah, but rotations, flips, all this, you can do it as many times as you want. It doesn't change the output because the logic is preserved. Color permutations as well. All right, so this means that, just from one training observation, you can get like 1,000 variants. This is impressive, 1,000 augmented variants. I wonder if the existing ARC-AGI solvers, once you incorporate stuff like this, I know Michael Hodel is doing his DSL, domain specific language. He's augmenting the training set problems with similar problems using DSL to generate similar output sequences. So with a domain augmentation like this, it is possible to learn a lot more because neural networks, they just add neural networks are pattern machines. Okay, are pattern finding machines. You don't find a pattern with just one example. You find a pattern with 10, 20 examples. I mean, human brain works the same way also, just that instead of just using the raw observation, we also have some form of thinking in us that helps us to find the patterns quicker as compared to raw observation. Okay, here is just raw observation. You just give more variance. And the ARC-AGI allows two different outputs. So the two most popular predictions. So basically what they do is from this variance, solve the variance and apply the inverse. So they ask the model to solve this, and then after that they do the mapping back. So it's like if you map to green, you map back to red again for the answer. So this allows the model to do multiple predictions for the same problem, and then you just take the top two. If you look at AlphaZero or AlphaGo, they also do translation, symmetry, augmentation, and also choose the best out of all predictions. So it's very similar to AlphaGo, in the sense that they are trying to, because sometimes the model has a certain bias for a certain kind of flip because he has seen that data more. So from there, you can get all the different permutations of the board and get the next move based on that permutation and then map back to the original board. And this is possible because if you rotate the board, you flip the board, it's still the same in terms of the logic of the board. Yeah, so similar, they do this, and they also do this for the Sudoku puzzles. They do digit permutations because you switch the 1 to a 2, and then you switch the 2 to a 1, it makes no difference in the puzzle because every row, column, and square, suppose we have 1 to 9 uniquely anyway, you just change the mapping, it doesn't matter. And for Sudoku, your mapping, because there's 9 digits, you can have 9 factorial permutations. So that's a significant amount of permutations you can have. Okay, data augmentation is disabled for maze tasks because there's not much to permute here. You can't permute the start and the end. Yeah, so basically the thing is you can use data augmentation to improve performance. I wouldn't say it's a bad thing, it's a good thing, but it's highly domain specific. I want to highlight here, highly domain specific. So you want to say HRM is great for general domains? No, it's not. It's great for that very specialized domain with data augmentation. So one thing I like to ask the authors is, if you turn off the data augmentation, how bad is the performance? How good or bad is the performance? And I suspect because it's only trained on this task, and there's only one task, it's likely it's going to be quite bad because it's not enough for the LLM to learn. All right, it's not like those kind of large industry pre-trained models you learn from other tasks. Here you only learn from this one task. You take away the data augmentation, you have really nothing to learn from. So it's a very highly domain specific model. Nothing wrong here, but highly performant if you give it the right input output samples. All right.
Sorry, can I ask a question, please?
Yeah, go ahead. Sorry.
I have two questions. First, so why using data augmentation is something considered not desirable? Because I think it's just a way of leveraging your existing data. Like it's still, if you can use very small original sample by augmenting it to a large amount and get better performance, I still think you can still say it has good sample efficiency. That's the first question. Yeah.
Yeah. So to answer that question is because if you are to pursue like AGI, artificial general intelligence, you may not know the domain you are working on, and hence you may not know how to augment your data. So this means that this is a highly specific to the domain kind of architecture.
Wait, but isn't I thought like translation, rotation, all these are generic techniques can be applied for any image, right?
to any grid puzzle. So here you are assuming that you only want to solve grid.
Can you give one example where it's a vision domain, but this techniques does not apply?
No, it's not the vision domain. Like for example, language. Like you want to ask a hotpot QA is an English language. There's no rotation and flip here.
Well, there's data augmentation techniques for natural language data.
Yes, yes. So I'm saying that this is highly domain specific. You need to already know your domain in order to do
So
your
by domain specific, you do not mean task, you mean modality, right?
uh and also task, because the same modality sometimes maybe rotation and flip may get it wrong. Like for
So
example,
I
if you
think
have some
there's like maybe there's some other vision task or these techniques is not very effective.
uh I don't think so, because if you do the inverse transformation back, you should be okay. Yeah,
So,
so
so that means these are still generic technique, just confined within a certain modality, right?
yeah, but like translations, then it will be task specific. If your task is to replicate the output drawing again in fine detail, you can't translate your picture and translate back.
Okay, so, let's just leave it here. Second question, when you say it's very domain specific, is there any like inductive bias that built into its architecture design that cause it to be domain specific?
No, not the design. It's just the augmentation.
Oh,
Yeah.
also basically you can still use this same model to for any task, right? But it's just not
I
at
wouldn't say
once.
any task, but any task involving input and output sequences.
Okay. So it's like transformer can be used to a wide range of tasks. It's just
Wide range of tasks, yes. I wouldn't say any task. Yeah, wide range.
so am I correct to say any task transformers can do it also can do,
Yes, it is a transformer.
but it cannot do uh all those all at the same time, right? So the distinction I
Okay,
want to
by
find
all at the same time, you mean whether it can do multiple tasks with the same model? Then the
yes,
answer is
yes,
no,
yes,
because
yes.
in this architecture, it's only trained with a task-specific data. But I wouldn't say that it cannot, because if you give it like multiple tasks here, so like if you, let's go back to the diagram here. If we give it like, for example, in the input here, we give it like tasks, like maybe like fill in the squares. Then you give it the grid. So right now it's only given grid tokens, but I wouldn't say that you cannot train with language tokens. You can.
But
You can probably train with a language tokens, like maybe task here is to change rate to grid, and then you give the grid. So so it's possible to and in fact you can take away the grid also. I believe it's possible to just use any input thing here. But the thing is, if you are using things like this, you kind of need to have semantic meaning for all this. And given that this transformer is not trained from any large language model, like it's trained from scratch, then you need a large number of samples to do this language meaning.
yeah, so also if you want it to be a generous model, I guess you also need to scale up the parameter count.
Yes, I believe so.
Yeah.
Yeah.
So basically, what they show here is for this architecture, you can have a very small model with very sample efficient training method, achieve some specific, very good performance on some specific benchmarks.
That's right. But I would say that it will be interesting to take this model and scale it up.
Yeah, that's
Yeah,
but they
they
didn't
didn't. They didn't.
investigate. Oh, I see. Oh, yeah.
But I mean, it's a great start for a initial paper. If the big labs use this architecture and scale it up, which I think they can, we might be able to see whether this low and high thinking would help to improve performance already in those industry level
Yeah,
models.
okay. Because my concern is like maybe there is some hidden inductive bias built into this architecture, made it such that it's very good at certain types of tasks.
Mm, if any, the inductive bias might be inductive to grids because all the tasks are grid tasks.
Uh,
Yeah, but I
that,
looked
that
through the code. It doesn't look like there's any specific grid embeddings. They use rotary embeddings, which are typical of large language models. There's no like really grid encoding that they use here. So I suspect it will be generalizable.
okay.
Yeah. Okay, let's move on to the visualization. I think all of you are quite interested to see this. So they didn't really show how to visualize the low level module. They only visualize the output module. And how this is done is by taking the high level module and feeding it through an output predictor, which is like the token predictor using the logics and predictor tokens. So here you can see this is the start state, and sorry, I think the red is the end and the green is the start. And you can see that as the maze progresses, this blue are the explored tiles. All right, so you can see that it's trying to explore from the inside, trying to explore from the outside, and it's quite amazing because all this, just take note, all these intermediate paths are not trained directly. Okay, we are only giving it we're only giving it the input, and the output that we are giving it is the output like this, which is the start and end with the path. So already, even though the training objective at each time step is being given the output here to do some backprop loss to see how close it is matching it, we don't train the intermediate thinking steps at all. Intermediate things you can see are like not in the path by itself, and in the end it gets stuff like this, and you see in the end it just connects the whole graph back like that. And all these things, there's no intermediate thinking annotation at all. There's nothing that tells the model, hey, you should connect the path by mapping the start first and mapping the end. No, nothing. It's just given the start state, given the end state, and then at each time step here, it has a loss that basically tells it to, hey, you should get closer and closer to this final output. And just with that, it manages to solve the maze. And I think that's quite amazing because like how they do the, the path finding and stuff, like it's not an algorithm at all. It's just them searching based on mapping to this end state. It's able to just prune out the wrong areas by itself like that without any algorithm. And to me, that's amazing because this is typically an algorithm task. But just by doing this recurrence, you can see that it solves bits of the puzzles at one time. So you don't have to solve it fully. Like recently, I did cover the IMO paper, IMO math, right? Prioritize the robustness of proof rather than the full proof. Because LLMs are not that great at going from start to end all the way. But what is great at is you can go start to intermediate, and intermediate to even more, and eventually you might reach the goal. So there's this stepwise improvement that if you can do it well, you can literally solve any problem. This is the art of problem solving. You solve bits at a time in the right direction. And here, given that we give the training signal, we give the final time step, which is the correct output, as the reward signal, it's able to have a goal. This last time step is like the goal to the training. It's able to get the goal, and you have a start state. And the start state is here. This is your first start state for the first thinking step. You also have start state 1, start state 2. When I talk about my architecture, learning fast and slow, I talk about training from any start state to any end state in the trajectory. And here they are doing that already. They are training from all the start states to all the end states in the trajectory like that. This is the reward signal. You take this state and this state, you see how far they are. They are already doing part of what I have envisioned in learning fast and slow. They vary the start state. The next step is to vary the end state, but it's a bit hard to vary the end state here because these intermediate states may not be correct. So they did the best thing they could do here. They just vary the start state. If you have intermediary supervisory signals, you can vary the end state as well. But just make sure the intermediate supervisory signals are correct. Okay, it's very bad to train on incorrect data, right? So just by training on the go, it can solve this. You can see the clear sort of thinking process as the final layer progresses to find the path. It's very logical, very human-like, I would say. Same thing for Sudoku. This is the maybe the final grid here, and all these red cells are stuff that are incorrect. You can see just by at first it just anyhow fills in the grid. They get some correct. It manages to slowly change the cells. So all these things in gray are the stuff that have changed from the previous time step. It's able to slowly change stuff. Of course, sometimes it changes things that still become wrong, and sometimes it changes the correct into a wrong one. But over time, through multiple changes, somehow it gets the right answer. And I think this is great because sometimes from here you can solve the question already, but you need to be able to evolve it slowly to solve it. And this idea of training it stepwise in order to solve the final answer, I mean, reminds me a lot like stable diffusion. You just keep diffusing at each time step towards the goal. There's stable diffusion. But of course, you can also say like it's iterative problem solving is similar. Very, very nice idea that you can just take any intermediate step, you give it the final output, and it can sort of like guide itself to its goal.
I think it's also kind of resemble evolutionary algorithm.
Yeah, it does. It does. Yeah. So like what's amazing is that my ARC solver can never solve stuff like this. It's so difficult. This ARC-AGI 2. You see, just by giving this thing here, and given the example output, okay, this is the test output, but you can imagine this to diffuse through the example output as well. You can see that just by giving the reward signal, it's like, okay, I think we should preserve this thing. It should be preserved. See, at first they tried to modify it a bit, then they realized, oh, dang, it's wrong. Let's get back slowly to the grid. And then somehow we have this rate squares also, so maybe we need to put in some rate squares here, more rate squares, and then eventually it gets here. It's like, wow, how is this done? There's no human language thinking at all. It's just thinking in the grid domain and having a reward signal that compares the difference between this intermediate thinking and this final thinking in the latent space. The reward is actually in the latent space. It's not in the output space. The supervisory signal sorry, it's actually in the output space. Yeah, they take the final output here and then compare to this output. Yeah. I guess you can also do it in the latent space, but I mean in this paper they did in the output space. So yeah, you can have multiple kinds of rewards, like what do you call that? Supervisory signals. Here you can see this signal has guided it here, and this kind of problems, very tough, right? You need to take away the diagonal stuff, which is it's not easy to express at all. You can see that it slowly diffuses, and then at first it gets some stuff wrong, but eventually it gets the right answer. And that to me is quite impressive. Like, so yeah,
Sorry,
that's
one more comment.
yes,
So it feels like, just to double check, it did not train on any kind of natural language data, right?
no natural language at all, and
Yeah,
that's probably why it can go 27 million parameters.
so it feels like, yeah, I think it kind of corroborate one of the hypotheses, which is it is not always optimal to reason or to solve a task in the natural language domain, because think of how human deal with art challenge. Do you think of the pattern in natural language? You don't, right? It's more of like a gut feeling kind of thing. So I think maybe exactly because of that, because the more popular more transformer-based model, they try to reason in natural language space, it kind of hinder or restrict this ability to solve more abstract reasoning, whereas this model like somehow bypass that problem. Yeah, yeah.
Yeah, you're right. And in any paper, your benchmark test usually help to buff up the model's performance in that domains because the model is stronger in those. Here, they did not pick any natural language domain because the model is good at grid. Like it's trained using grid sequences. They flattened the 2D grid into a 1D sequence and fed it in, and output is a 1D grid sequence as well. And this is basically like the kind of input output that they can do. And they use the examples that can do grids as well. So here you don't see any natural language because they didn't train on natural language. Yeah. So, but that aside, it means that you can do reasoning without language. Okay, maybe I just pause here for like maybe 1 minute for anyone else want to add. If not, I will go through why language may not be needed for thinking. All right. Um, Maybe any questions, any comments before we move to the next part?
So just wanted to add a comment that to add to what the other person said. Thinking out in token spaces, like thinking out loud, like you and I are discussing, but a lot of the times it's just inner monologue and just silent thinking in latent space. That's what this one is doing, as opposed to always using a whiteboard and speaking out loud and trying to reason through that, which is very inefficient. And humans don't do that.
Mm.
Not always.
Yeah, not all the time. We typically reason in language if we want to do like philosophy and stuff. But if we are talking about like visual understanding, it's very hard to visualize an image with words. They always say an image is worth 1,000 words. In fact, actually, it's more. It's very hard to describe to you something that is new to you. Like I had to use a lot more words to convey that. Whereas if I show you a picture, you might get it instantly, right?
And the paper also mentions this. They say that language is more a means of communication. Of course, you can use it to think out loud. Like, for example, in our case, all of it is going on. There's inner thinking going on in my head, in your head, and we are also thinking out loud across brains, two brains and multiple brains. I think all of this is needed. Maybe this could complement the standard LLM, in the
Yeah.
future, maybe. Yeah.
Okay, so let's cover through how thinking is done in traditional LLMs now. So this is the first paper of chain of thought. I mean, of course, I think there might be previous ones, but this is the first famous paper on chain of thought. All right, so this basically says that, you know, a natural language model trained in input and output sequences may get math wrong, okay? Because like here we do a few short prompting, we do question answer here, and the answer is 11. There's no intermediate steps here. But if you just prompt the intermediate steps, oh, okay, there's 5 balls, 2 cans of 3 tennis balls is 6, 5 plus 6 is 11. You know, you list out the intermediate steps, you can get the answer. Okay, I mean, here, you get answer is 9, okay, compared to the initial model here. So when this first came out, this prompted a lot of people to recruit teachers, you know, to come out with model answers, and then you train those on the model answer. I'm sure OpenAI recruited a lot of PhD students as well to train on reasoning for their O3 mini or their O1. Yep, they also recruited people to train on code. All right, lots of code. That's why OpenAI code is actually not bad. A lot of code benchmarks they have used, and they recruited people to write good code. So this is something that, you know, is quite reflective of the training data paradigm of large language models, because large language models is like, you know, your data is key to what your model can output. If you give it garbage data, it gets garbage output. If you give it good data, you might get good output. I wouldn't say always get good output. You might get good output because it's always a next token prediction is a stochastic kind of thing. And yeah, so this is something that chain of thought can help. You give it the thought itself, and you ask the model output in this format, and you know, you can get better reasoning. Like there's also zero shot chain of thought. Like zero shot reasoning is like when they say like, let's think step by step, or like take a deep breath and solve the problem, and think step by step. Wait, let me. So people have come up with prompts that, you know, try to help the model to like reason better without this kind of in-context prompting. That's the next level. But typically, the thinking and the reasoning is all still done using language, right? This is something that is quite common because the predominant paradigm for LLM is language. We use text inputs to text outputs. Okay, but now that is changing. Okay, now we have multimodal inputs to multimodal outputs. So the LM might be able to think in images now. All right, it's able to generate entire storyboards of images because it can use the image tokens. So we are seeing a paradigm shift right now, but this is the traditional chain of thought. Okay, so Yann LeCun once wrote a paper with Jacob Browning, and they gave quite a strong case that language alone will not be enough to approximate intelligence, because there's so much more to human intelligence than our language itself. All right, here they use very strong language. From even trained from now to the heat death of the universe, we will not be able to approximate human intelligence. I think that's overly strong, because, you know, we might be able to approximate some human intelligence with language, because some language is enough. Like for example, if you want to talk about, you know, talking about, you know, like philosophy, maybe in language is maybe enough already. Yeah, but or sentiment analysis, you might be able to use language, and that's enough. But one thing about language is that the models does not experience the world. Okay, it's at best an approximation of the world. It's like you're reading all about zebras, but you don't live the life of a zebra. The best you can do is to use those words that you have read about the zebra, and come up something with it. Or unicorn, what is a unicorn? We don't even know. There's no such thing, right? But you can say, oh, unicorns have horn, they are horse, they can fly, you know that. But how does it feel like to be a unicorn? How does it, what will a unicorn do when it goes through a cliff? You know, can it fly? Can it we can only base our understanding on what we have read, because we have no experience of it. But I talk about humans. At the edge of a cliff, can you jump to the other side? Probably not, you know, unless you are Neo, you can fly across the matrix, that kind of thing. Probably not. You have some experience about the world, you know, gravity and physics, right? So world models are not there for large language models, and it gets physics horrendously wrong. Physics is usually the worst, okay, the worst output example for LMs. You look at video models, the sometimes the person can run backwards Okay, it's how to run forward, but the thing run back because the idea of physics is not really well appreciated. Like for language itself, you ask common sense reasoning, like if you drop a ball off the bridge, where will the ball go to? Some people say go back to your hand, but actually you should go all the way down the river or something. Some people have done tests on this. It is a weak point of large language model because it is not in the training set. The training set does not have physics inside. We don't have a simulation of the world. We don't have a world model for it. So yes, language may not be enough because you need to have an understanding of how the world behaves. You need to have some idea of vision because large amounts of our intelligence is based on vision. You take away vision, just using words alone, you may not be able to describe a lot of things. Embodied information, like how you walk. Some people don't have this, like sensory motor is how your muscles and body like behaves. There's also another thing, proprioception, where basically it's the feelings of where your muscles and hands are and your legs are. People who have damaged a certain area in the brain that affects proprioception needs to keep constantly looking at their legs to figure out where they are, and they find it very hard to walk. So like if you are doing stuff like embodied systems, language alone may not be enough. You still need to have your sensor information about where your robot arm is, what's your robot touching, what's your robot seeing, and so on. Language is not enough. You need the sensory motor information. Your context that you are in, social cultural context, also plays a part into interpreting this language. Like for example, in certain cultures, thumbs up is good, maybe good, but certain cultures, thumbs up may be offensive. And sometimes you can say, oh, that was great. Is it sarcastic or is it normal? You don't know. It depends on your culture. Like, good job, bro, that kind of thing. Sometimes people find it offensive. Sometimes people find it's great. And language alone, without the context, is not enough. But of course, this social cultural context can be built in language as well. You can say, oh, I'm in this country and this is what I heard. Then, you might be able to build in. But there are a lot of things that, like vision, world models, and so on, that you can't build in traditional LLMs because language is not enough. Of course, this visual understanding is slowly improving. You can put visual tokens already. Okay, so you might be able to mitigate some of this. But in general, using language to reason has its limitations because language is probably not the most rudimentary way of reasoning. Right? It's probably a way to communicate. And, the way that our brain works, a large part of it is subconscious or unconscious thinking that has no language equivalent to it. Right? It's like, uh, asking you to interpret assembly code. All right, assembly code is a kind of low-level programming language. How do you interpret assembly code in language? You can say, oh, I shift this data from buffer 1 to buffer 2, and then I copy it. It's like you can describe all the low-level steps, but what exactly is it doing? Oh, it's doing bubble sort. You want to describe that in low level. You want to describe all that. Shift these two numbers if it's greater, then you might take 1,000 instructions and you might still not understand what's it because you just literally just translating the instruction. Whereas, like at a high level, you might be able to say, oh, this is doing a sorting. And all this is very hard to express in language. It might be easier to just look at the state of the buffers and understand what's going on by that. All right. Gavin, you put your video on. You wanted to say something?
No, I agree. I mean, there might be people who will debate. Ilya Sutskever will say, language may be okay to do some amount of approximation because some of the cultural context gets picked up during pre-training. But you can never be sure. But for the most part, I believe that when it comes to physics and stuff like that, they really struggle, and it's just wasting a lot of unnecessary parameters trying to do this via language. It's just like a crutch. Yeah.
Correct. So the question we want to ask ourselves, and the question that this paper is asking, is can we think in non-language? All right. So the traditional paradigm, you have an input instruction, you have human language, and then you output your thoughts, your chain of thoughts. Right. The most famous is the REACT framework, reasoning and acting framework. So what they do is like you have an observation, and then you have your thoughts, and then you have your action, and then you keep repeating this again. This is typically the fundamental framework for almost all agentic systems out there. So if you want to build an agentic system, this is all you need: observation, thoughts, actions. Do the action, then you do observation, thoughts, action again. So if you just do stuff like this, you can get some thinking in terms of this thoughts here. You might be able to get some explanation about what's going on, but that's only if human language can express the action well. If you want your robot arm to move 22 degrees up, that's not going to cut it. Like, it's very hard to express this in language. But, if you use an intermediate latent space as your thoughts, like in this case, your thought space is nothing to do with your language at all. You have no need to translate it back to input. You take your input, your grid, go into grid tokens. The semantic space of the tokens will use to fuel the thoughts again. And then this thoughts actually is in latent space, is in the hidden vector of the Z low and Z high you saw earlier. You keep doing this again and again, and eventually when your model is confident enough, it outputs something and outputs back in the original domain. So your entire thinking here is done in latent space. No need to map back to language. And that is, to me, a huge achievement of this paper, because I think this is something that is challenging the paradigm. I know there's a few research labs, like some in NUS, like Brian Lowe, Prof. Brian Lowe, he has some chain of thought in latent space. And so I think people are exploring thinking in latent space, and it's proving to be quite powerful, because by thinking in latent space, you don't have to map back and suffer the compression loss of going back to language. You can just use the latent space itself to condition your next thinking.
Sorry, I want to make a clarification here. So I'm also seeing some paper from, I think, from Meta on doing reasoning in latent space, but I think there's still a very important distinction, because in this case, the latent space is not related to language at all, whereas in the still more traditional LLM case, the latent space is the latent space of the learn from natural language. I think the advantage there is in latent space, it is continuous, it's not discrete token. So there's a certain advantage compared to reasoning in the token space, but it's still very different from this case. Where there's nothing, the latent space has nothing to do with natural language, right?
In this case, the latent space is not natural language, because the input space of the HRM is not natural language.
Yeah. So I think that's still a very important distinction to highlight.
Correct. But if you scale up the HRM to natural language, it is possible the latent space will be related to the human language.
Oh,
Because latent space depends on your input, you see.
yeah, but I thought the reason it can be very good here is because it get rid of natural language. I think of it as an advantage, not as a weakness.
It's advantage for small models, but I think if you want to use this hierarchical reasoning model in more everyday life tasks, you have to have human language inside. If not,
Okay, then I
uh,
think then we need to see when in that case, can it still score well on
correct.
pass on the ARC challenge? Yeah.
I'm positive actually it can. You just need to have a larger model. Yep. So this one, of course, I'm sure the big labs will be probably experimenting with it. We will hear some news about it soon. But the main thing is, you can think about human language. So like chain of thought is the one with human language, right? Reasoning, it externalizes reasoning via a generated text, while latent reasoning uses a hidden state. Okay, this is not in the paper, by the way. I just summarized 2 paragraphs into this table, all right? So domain of thought, all right, it relies on human defined languages. Like, so they have found out that, like in chain of thought, if you get your sequence of reasoning steps wrong, it's disastrous for the LM. Like, instead of saying that step 1, look for groceries, step 2, buy them, you put step 1, buy them, step 2, look for groceries, you get the question wrong. Okay, but in the latent reasoning model, sometimes maybe your steps are, okay, they didn't say that you can do that, but I think latent space is a bit more robust to sequential errors. You can see in the latent space thinking, sometimes they do the wrong step, but can map back again. So, and also one thing is, because there's no need to translate back to human language, you can actually do more, all right? Because you are not constrained by language at all, right? Maybe you can talk about, I need to translate this square from left to right. Okay, human language can express it, but what if I say I split the square into 4 parts, each part goes one here, one there, one there, one there? It can be hard to express in language, but in the latent space reasoning, you might be able to do that because it's interpreting things in terms of the native grid itself, all right? So you can think more. Data requirements, chain of thought needs significant training data, and that's why people are doing those kind of things like, you take your data, reasoning trace, and you train on the reasoning trace. Okay, the most famous example is DeepSeek V3 and DeepSeek R1. DeepSeek V3 generates the base model. DeepSeek R1 takes the reasoning trace, gets more, and then trains back DeepSeek V3 again to, the reasoning trace gets trained here as input data, and you keep training this. This is what the huge labs are doing. O3 Mini also trains the model on the reasoning traces produced by the model. One bad thing about this is that if your reasoning traces are wrong, you reinforce the wrong things. So it must be very selective about what reasoning traces you use. And typically you only use reasoning traces that are verifiable, like math problems. You know the answer is correct. Most likely the reasoning trace is correct. Hopefully, because you can't verify the reasoning trace that easily. All right. So there's a lot of problems here. Sometimes the model might even, I'm going to do a discussion on this, and the model might even hallucinate the actions done because of this training on reasoning trace. Because, I've noticed some models might say, oh, I've searched the web and I found that this is done, but they haven't actually called the web search tool. It's just because the LM is trained on the reasoning trace of web search before, it just hallucinates it has done the action already. That is disastrous. You don't see this stuff happening much if you use models that are not trained on reasoning traces. But for those models that are trained on reasoning traces, they hallucinate action even more. In fact, the 0304 technical report by OpenAI shows that they hallucinate more than the 4.0 mini model. Yeah, so there's a risk of hallucination here when you train on reasoning traces. And this is an inherent problem with chain of thought. Because you need to train with significant data to, say what steps to follow, what thoughts to follow. You want to automate this process, you incur the bootstrap error. You might bootstrap wrongly. So what if you can train the reasoning without chain of thought, and that is latent reasoning. You just take, you just typically, as what I showed just now, you just take the input grid, and then you compare to output grid. And then, from there, you can take the intermediate grid, and then you compare to output grid. You can do that for every single time step. And, that is sort of like reasoning, because like you are reasoning how to get from this intermediate state to the output state. And if you can express everything as grids, sure, you can use HRM to do it natively. But if not, I'm sure you can train HRM with language as well, to initial to output, intermediate to output. I think they can do it as well. I mean, it's ultimately still a transformer architecture. It just depends on what input and output you give it. All right. You might need more training data, yes. But this architecture has shown us that chain of thought by human annotation may not be needed. You just need the input and output. The model can learn how to reason by itself. Okay, response times. Quite important here. Response time is very slow in chain of thought because you need to output the entire reasoning traces. But in latent reasoning, it might be very fast because all these are done in the vector space. And vector space is much faster than you generate one token at a time in an autoregressive manner. In chain of thought, that's what you do. But one thing for sure is that chain of thought allows for tool use. Okay, this latent reasoning does not allow for tool use because there's nowhere to fit in that tool output into the model again. I mean, unless you stop the model as snapshot, run the tool, feed the tool as a hidden vector. So I think it is possible. It's just not done yet. So I have a slide to show that, I think it's possible to integrate this chain of thought reasoning with your latent space reasoning. I think it's possible to integrate both of them together and get a hybrid model. All right. So this
I
yes.
comment. So
What is there
I
another
think
question?
it's
Sorry, wait. Let's one at a time. Maybe Zeri, you say first because you started first. Then Arvin, you do it later.
so I think it's almost expected for a reasoning model to hallucinate more because simply has more tokens, so there's more chances to fail at each token.
More
Yeah,
possible for reasoning models to hallucinate more because there's more tokens. Yes, in that sense, you're right, because like latent reasoning just outputs the output, right? There's no reasoning outputted. So
no, sorry. Firstly, I'm comparing to like non-reasoning language model.
okay, then in that case, if it's just both models are just outputting the output, then the chance of hallucination is the same, right?
No, because reasoning model has longer output.
It depends on how you prompt the model. Like sometimes you
No,
just
no,
prompt
no,
only the
simply
answer.
because you have more reasoning traces. I'm not talking about the non-reasoning part. I'm talking about the entire sequence, which includes reasoning trees.
Oh, but non-reasoning models, you can just ask it to output the reason without any output the final answer without any reason.
Yeah, but I doubt that's how they conduct the test, which type of model hallucinate more.
I think the hallucination part really, you're right. The more output tokens, the more chance of hallucination. The more reasoning done, also the more the chance of hallucination, because there's just more steps, more points of failures. Yeah.
Yeah, and another thing is, I'm not sure. I'm still not sure if latent reasoning is the way to solve it, because from what I see, hallucination is more of a problem of the natural language. So even for this model, if you train it on language data, natural language data, the same thing might still happen. Currently, it doesn't hallucinate as much because there's just not enough data for it to approximate very complex distribution, right? Because at the very core, the hallucination is just looks very plausible output, which is not actually correct. The reason that happens is because the actual distribution is so complicated. So you can have many different ways of generating some very plausible sequences that looks correct. But that happens on a very large scale. Then you can have that. But for very domain specific, like in this case, you don't even train on language data. So I think the chance of that happen is very small because of the scale. I'm not very sure if if latent reasoning can address that issue.
I see. So you are making a point that this paper doesn't use language, hence the hallucination rate is lower compared to using language, and we will
Doesn't
find
use
out.
language and on a small scale because it train on very small amount of data.
Of course, that I cannot comment because we don't know. We
Yeah.
need experiments that that does language using this latent reasoning model. Then we will know for sure whether this works.
Yeah, I'm not saying that's definitely the case. It's just my educated guess.
Yeah, yeah. Okay, Arvin.
Interesting point. Yeah. So I was trying to make a point. This may not be the right slide, but since you have all the advantages and on the latent reasoning column, I thought maybe the amount of compute you need is also something that you could call out, because I think for the Sudoku they use like a laptop GPU, like a RTX 4070, and train for 10 hours, and then it's get perfect scores. That seems remarkable, given how much of compute requirements are there for the traditional, uh, you know, LLMs.
Yeah, yeah. So this is something I think compute-wise, latent reasoning is also much less compute because you don't have to. Maybe the reason for much less compute is no language, no human language. Yeah, maybe. But you don't have to actually reason. Because one thing is if you use chain of thought, your token length will be higher. So your increased token length, and also like at every intermediate thought, you need to feed in the entire previous context. So that also takes up compute, and it scales up quite fast if you have like 100 to 1,000 reasoning steps. Like agentic systems do thousands of steps or hundreds of steps. Soon you will find that you lose the context. Like if you use Claude code, for example, after a while Claude code will output nonsense because it loses the context. So those stuff can be solved with like 1 mil token models like Gemini models and the recent OpenAI models. You might be able to solve that to a limited extent, but still 1 million will still be hit after a while. And yeah, I find that for larger context length, you have a higher chance of getting an output that is an error. All right, so this increased context length is not ideal. Doing it in the latent reasoning part, you might be able to, because you have a fixed size hidden vector, you sort of like do auto summarization in some sense. Like you don't have to say summarize your hidden context. You are forced to summarize. You only have a fixed vector. So there might be some kind of good points of doing that. Although, you might say that, hey, why can't I put all my reasoning as a transformer input sequence again? Like, why can't I do the recurrent step as a transformer? Then you have a transformer. Instead of saying a recurrent transformer where you recur the transformer multiple times, you can do a transformer recurrence, use the transformer to model the recurrence, and use the transformer to do the actual steps. I mean, I don't know whether people have come up with transformer. I mean, I'll call it transformer square. Like it's entirely possible to model the recurrence as a transformer as well. That's one.
Transformers in a loop. Yeah.
Yeah,
So,
transformer inside.
The low level benefits of the queries, keys, and values are definitely coming out, and then the structure of like a boss guiding the worker, and the worker is doing multiple steps. I think this. I think there's a few more things they did in the paper, like having segments, like you take a long time to think, and how many time steps to think is also dynamic. They use a separate Q learning
Yes,
head to
yes.
determine. That was amazing. And then to get rid of the BPTT. Back in the day, we used to work with RNNs quite a lot 7, 8 years ago, and it is such a pain to train those models. And how you kind of get away with that with this one-step approximation. Some of those things in the paper also, I think, were pretty remarkable and worth calling out, maybe.
Definitely. So I think today I don't think I have time to cover everything. There's a lot more to cover actually that are quite interesting. So maybe what I want to do is I'll just want to maybe end on like maybe this slide and also give an overview of what we will cover the next session. I wanted to cover everything today, but I think discussion is more important. It's great. I learned quite a lot from you as well. So I'll just cover this slide and one last slide, and then we can end for today. So one thing that they managed to show in this paper is that, if you were to scale your transformer, and like they realized that scaling depth is more important than scaling width. All right. So you see this scaling width, you can scale the width of a transformer and it still can't solve Sudoku. And that's because most of the reasoning is iterative reasoning. You need the depth to think about stuff. You can't just compress all your reasoning into one time step. Like it'll be quite amazing if in one time step, think from the start board to the end board, I solve it fully. That's also not possible for algorithms. In fact, for algorithms like depth first search or like dancing links algorithm, still need to do some iteration, you intermediate step, you look at the intermediate board, you try again and so on. It's not done like that. It's not magic. So you need to scale the depth. And the depth scaling, okay, you can scale to a certain level and it plateaus. All right, this reminds me a lot, like, before we had ResNets, residual networks, we have layers upon layers. Okay, before ResNet, let me just put there. Before residual networks, we have layers upon layers of MLP, multi-layer perceptrons. Yeah. So, and after a while, there's a vanishing gradients, exploding gradients, because your gradients just get accumulated to a point that it either goes to zero or it gets so large it destabilizes the training. So people have come up with this idea, a very, very interesting idea, or like basically if this is your layer, all right? So instead of just going through many layers at one go, I can just, going through your layer like that, instead of just I have a skip connection here. Okay, so then your next layer here, you can have another skip connection and so on. So this idea, nothing much to do with the brain, actually. It's more to do with a backprop. And actually this paper's idea is also nothing much to do with the brain, also more for backprop. Like you need to target the idea that, backprop cannot do multiple recurrence well. Because after a while, the gradients, if you take, for example, the gradient is a 0.1 for one time step. You take 0.1 to the power of 10, you get something that is approximately 0 already. So this is vanishing gradients. Okay, you take a gradient that is about like 1.1 and then you go to the power of 10. That's approximately, I can't remember, but like 100,000 or something. Someone can go and punch and calculate. It will go huge very fast, okay? Approximately a large number, okay? Large number. Okay, I don't have the calculator right now, can't calculate this. So this is a trend. When you do a recurrence multiple times, you don't scale well. And no, transformers also have layer norm or batch norm. You can also like normalize the output gradients. But the fact is, if you scale the depth even more, that may not be enough, right? Because you can have all your normalization, but if your norm is quite large as well, you can scale down the variance and so on. Somehow it doesn't scale that well. Yeah, I mean they tried this. They tried to scale the depth, and you can see that it's not that great. Recurrent transformer is basically saying that, hey, I don't just use a transformer, I also have a recurrent loop to store a hidden state per time step. Okay, it's similar to this paper, but this paper has two hidden states. Recurrent transformer, you store one hidden state. Yeah, the recurrent transformer paper is quite cool, by the way. They have a visualization, take the transformer like that, and then they and then you can go see the GIF. Basically, they're saying, what if we can make the unit of the recurrent neural network a transformer? And then they show the so you can see it's actually an improvement in terms of the stuff it can contain, but it's not enough. It's not enough.
But do they do the back propagation through time in that to go back all the way?
Oh, that I didn't know, but I think they did backpropagation through time for more than one time step for
Understood.
recurrent. Yeah,
But this one they get around that whole problem in
correct.
this. Yeah.
This hierarchical reasoning model, they use two hidden states and they don't just do recurrence. So maybe the low level recurs all the time, but the high level recurs once in a while. And somehow it solves the gradient problem. And that's remarkable. Yeah, that's remarkable. We can go through the math more in detail next week. But I think the idea of using a fast learning module to perhaps store more updates, but that one may be a bit low level processing, and a high level module to take those low level updates once in a while. The key is once in a while. You don't want to take this every time step, because if you take every time step, you will lock in the gradients very fast. Like the gradients will change really fast for both. So you have one that the gradients change quite fast, one the gradients change a little bit. And somehow using this truncated backpropagation through time, which I will cover more in detail next week, you just don't backpropagate everything. You just backpropagate only the final state of the L module, final state of the H module, your output embedding, output mapping, and your input mapping. Just backpropagating through four things in this transformer architecture, in this hierarchical reasoning module, you approximate almost the same gradient as you backpropagate everything else. They use some math proof to show it. I'm not going to cover the math proof because I think there's no point backpropagating all this. Like it will just incur a lot of vanishing exploding gradients. They bypass this by just backpropagating through the final layers. So if you ask me, is this how the brain learns? My answer is no. Okay, because the brain does not use backprop. Okay, as much as people like to say, there's no evidence of backprop being done in the neurons of the brains. And this is because biological mechanisms are not so complicated to model differentiation. Yeah, we model by concentration of chemical gradients, increase of calcium ions in the cell membrane, action potentiation. By learning with calcium ions, you just get more gated channels to intake sodium and potassium ions. It's not easy to model those in math, but one thing neural network does is that it models everything in terms of a mathematical equation, which is easier for computers to compute. Yeah, one day maybe you can model the level of the neuron, but I think that's not enough, because I do think that there's more to physical world than there is. So we might even be missing something, even if we model the entire chemical gradients and everything. So I'm willing to accept math as a replacement. You don't have to model exactly. And if we use math as a replacement, gradient backpropagation is very important. And I can't believe I'm mentioning this again, like 3 to 4 years after the ChatGPT paper came out. Because when the ChatGPT came out, I have a video on ChatGPT. I talked a lot on the gradients. Even before ChatGPT, I was already streaming on MLP, CNNs, multi-layer perceptrons, convolutional neural networks. It's all about gradients. It's all about how you learn from gradients. The whole deep learning world is about how you learn from gradients. So it's quite remarkable. You have a new architecture that can scale. And this is not trivial, by the way. This performance gain is not trivial. This is like a ResNet moment, you see. Like 100%, you can get 100% on this problem just by using this. That's remarkable. Yeah. All right. I see someone wanted to speak. Did I see wrongly? Or yeah.
No, this was fantastic. Yeah, great start.
Yeah. So let me just end on one slide, and then that's a like primer. We'll be talking about some math next week. I think I want to talk a lot more on like how they can do Q learning for adaptive stopping, but I don't think it's that great because the results don't show that it's performing better than fixed. Okay, and like some of my thoughts, but I'll skip this for now. I just want to end on this slide here. What I want to say is that right now in chain of thought, we have our intermediate language as language, intermediate thoughts as language. But in the hierarchical reasoning model, we have latent space thinking, and typically it's a latent space of the grid space because there's no language in it. But moving ahead, we kind of need a hybrid, because if you want your LM or your whatever HRM, the system to be useful for you, you kind of need to talk to it in language. It's going to be very hard for us to talk to it in grid tokens. Like not all tasks are grid tokens, you see. You need to be able to talk in language. So over here, maybe instead of input grid, we have input grid, input language, or input domain. Very, very universal. Yeah, you don't just want to constrain it to grids. And the cells, you don't want to have grid cells only. You want to have like language, image, video, audio, sensory motor, like whatever that can be used to represent your input domain. You want to have it here. I think transformers are going quite well into this multi-modality domain already. We need to keep improving it. And the thoughts itself, right now, all the thoughts are done in the language space. What I'm thinking is that because we have shown that this latent space can do quite well, why can't you just do like a recurrent transformer kind of architecture? Put the latent space inside and do your recurrence loop. Your tool use can either be in your language space or in your latent space, depending on how you want to do it. But with this architecture, you can reason both in language, which might be useful for some problems, or you can reason in latent space, or you can do both. All right, and then the output can be any of these tokens. So this, I call it the universal thought machine. I don't know whether there's any name for it, but the idea is that you can reason in whatever domain that suits you, and you don't even need to train it to say, hey, do it language or do latent space. Your input output data can guide it to choose the latent space needed. Like this part here, ideally, non-supervised. Like you don't want to supervise your intermediate thoughts. You want to let it maybe just condition on the final output. You let it learn by its own self-supervision, or like basically the reward signal is only the difference between this intermediate output to your final output. You can just supervise like that. And like what the HRM is doing, you don't have to do extensive chain of thought by human language. In fact, this language here is maybe model generated language. We don't even train with the human language. We try not to touch the reasoning process at all, because the moment you incorporate human-based reasoning inside and you train on the human-based reasoning, there's bias. Like, so you see like O3 models or O4 models, they solve complicated problems well, but they also are not very good at solving simple problems anymore, because like you give it a simple problem, like that is Tom is Timmy's dad. What is Timmy's relationship to Tom? And because they train it on a lot of those kind of logical puzzles, then they say like, oh, Tom is Timmy's father's father or something. Yeah, it becomes harder. But actually, it's supposed to be, if Tom is Timmy's dad, then Timmy is Tom's son. It's a very simple relation. But if you train with reasoning traces of solving complex logical puzzles, you might overthink things. So maybe training like chain of thought on the intermediate language using supervisory signals, like using human annotated thoughts, may be something not ideal. So it might be a thing of the past. Like maybe just taking the input to output, letting the model reason by itself, maybe the best bet. Of course, I don't know for sure whether this can be done, but at least for grid, HRM has shown it. Okay, so I just want to end on this slide. I think we are seeing a paradigm shift of how we think or how the models think. And we are slowly discovering that human language is not the best way of thinking. Yeah, it is a good way of expressing our knowledge to each other, but it may not be the best way to think about problems. Okay, comments, things. If not, we will end here and hope to see you all again next week. We will have actually quite a lot of discussions over here. I just don't want to shortchange it because it will take a while.
Absolutely. Yeah. Great start though. Thank you.
Yep. If not, thanks so much for coming. I'll see you all again next week then. Okay, bye.
Bye.